Namaste. This is Nataraja Pillai again. Um, Today, we will discuss something on viscous interaction, right? So, I hope you have gone through the thin shock layer, entropy layer, and in the entropy layer, there is one vorticity interaction. Right? So, let us start with the information. So, I acknowledge Anderson's hypersonic and high temperature gas dynamics. Um, so these characteristics of hypersonic flow we are discussing, right? So already we had a discussion on the thin shock layer, right? Then entropy layer. Now we will discuss the viscous interaction, right? So in the coming classes we will go through the high temperature flows and the low density flows, right? So, a small recap on entropy layer. We know that there is a entropy layer is because of the, from the nose you have a strong shock and then further you have a weak shock, and the uh, entropy is like change in entropy is proportional to the vorticity based on Foucault's principle, and hence there is a formation of uh, entropy layer, and that entropy layer in turn creates the vorticity, and already we know that in the boundary layer we have the vorticity. So these vorticity, because of boundary layer and because of the entropy layer, interacts with each other and creates a vorticity interaction, right? So that is what we have inferred from the entropy layer. Now, let us come back to the viscous interaction, right? Say, in this, consider a boundary layer, which is for a flat plate in a hypersonic flow. We have, there is a boundary layer, edge, and we have a um, temperature profile, right? Typical temperature profile, and say the temperature varies with respect to the y direction. The consideration here is the Mach number is very high, right? Now, there is a point, right? When there is a formation of boundary layer, right? So, the formation of boundary layer, what happens is that the flow velocity slows down in the boundary layer. We know that at hypersonic flow, the velocity is really very high. It means that of mv square, we can consider the kinetic energy. So the kinetic energy will be very high. So very large amount of kinetic energy is there, and because of the boundary layer or the viscous nature, it slows down. Now the question comes where that slows down, the slow down kinetic energy when. So the last kinetic energy is actually transformed into internal energy, right? So internal energy, it is in this case it is necessarily the temperature. So this phenomenon is called viscous dissipation, right? So part of the last kinetic energy converted into the temperature, right? So the characteristics of hypersonic boundary layer are dominated by such a high temperature increase, right? So here in the viscous interaction, we have one point called viscous dissipation. That is the kinetic energy necessarily converted into internal energy because of the viscous nature inside the boundary layer, right? That in turn increases the temperature inside the boundary. Now, say let us have example, the viscous coefficient increases with the temperature, correct? We had a discussion on probably fluid dynamics or fluid mechanics in third semester when we start about the coefficient of viscosity, kinematic viscosity, and all those things. We had a discussion on what happens when there is the effect of temperature on air and water, right? So the viscosity coefficient increases with the temperature, right? Um, so what happens is that makes the boundary layer more and more thicker, right? Again, here in addition, because of the pressure is constant normal to the boundary layer, the increase in temperature again leads to the decrease in density, right? So the decrease in density, so basically rho is equal to P by RT, where R is a specific gas constant, right? So the temperature, because of the increase in temperature, there is a decrease in density rho. So the decrease in density rho now have a problem, right? So to pass the required mass flow through the boundary layer at a reduced density, the boundary layer thickness must increase in order to pass the expanded or changed density flow, right? So what happens is like it increases thickness of the boundary layer again, right? So both these phenomena, they combine to make the boundary layer of the hypersonic flow to grow more rapidly than when compared to the low speed flows, right? Please remember 2 points. One, we had a discussion on viscous dissipation, and the second one, we had a discussion on heat density, right? So both these makes this particular hypersonic boundary layer grow more rapidly. Uh, Again, the flat plate compressible boundary layer thickness delta, we can say the delta is a boundary layer thickness which is proportional to the square of the Mach number m infinity by the square root of the Reynolds number. The Reynolds number Rex can be the local Reynolds number. Anyway, we will discuss about this laminar boundary layer thickness and we will derive the same in the later classes, right? Now, so we know because of the variation delta varies with respect to m infinity, it can become very large, right? It can become large at hypersonic speed. Now, it is not simply about the boundary layer getting thickened, right? The thick boundary layer, right? Here we have a thick boundary layer. We already have convinced that there is a thick boundary layer. The thickness is because of the kinetic energy necessarily converted into thermal energy as well as the density. The density want to move within with the given space, so it thickens the boundary layer like that. So the thick boundary layer in the hypersonic flow can exert a major displacement effect, right? The displacement effect to the inviscid region above this boundary layer. Inside the boundary layer, we can say that it is a viscous region, and above the viscous region, there is a inviscid flow, right? So in the inviscid flow outside the boundary layer, it creates a displacement, right? Now, what happens is because of the displacement effect, the the effective body shape changes for a particular hypersonic wave, right? So because of the thickening boundary layer, there is a displacement effect that makes the body more thicker. The hypersonic body become more thicker. Again, um, say because of the extreme thickness of the boundary layer flow, the outer inviscid layer is greatly changed. This change, what happens is now the boundary layer gets thickened and it disturbs the inviscid region. Now the inviscid region also give a feedback, right? It also in turn give a feedback to affect the boundary layer. Now imagine the boundary layer gets thickened, inviscid layer opposes, boundary layer gets thickened and the inviscid layer opposes. What happens? There is an interaction between this boundary layer, right? This boundary layer from the viscous region and the outer inviscid region. So this interaction, we call this interaction as viscous interaction, right? So such extreme thickness creates the boundary layer flow, right? Makes the interaction between these two layers, right? So let us discuss about the viscous interaction here, right? Now, the viscous interaction, as usual, you know that the viscous interaction can have the important effect on surface pressure, right? Now you know when there is a change in surface pressure distribution, then the lift force, drag force, stability, and all those aerodynamic parameters will change, right? And again, more skin friction and heat transfer are also increased because of the viscous interaction. Right? Here, in the first point, we consider that the change in surface pressure distribution. The surface pressure distribution is because of the interaction, viscous interaction, right? And the lift force, drag force, and the all other stability and hypersonic vehicle based on the surface pressure distribution, and hence this also gets affected. So this is what the viscous interaction on a sharp, right circular cone at the 0 degree angle of attack, right? So this is what the interaction effect we have, right? So PC is the pressure to the cone, and the P is the pressure, right? So here the pressure distribution on the cone, right, cone surface is P, and given as a function of distance from the tip, right? So if there were no viscous interaction, the inviscid surface pressure would be constant and equal to PC. Once P and PC is equal, then it will become 1, right? So in the case of uh, P by PC, if it is 1, it means that there is no viscous interaction. Now, assume that there is an interaction, right? There is a viscous interaction. So the pressure near the nose is considerably greater, right? Considerably greater when compared to the other surface. Right? So the surface pressure distribution, it decays further downstream and ultimately approaching to the inviscid value for downstream. Right? So this is what the graph is between P by PC and the X. We usually do that in the airfoil X by C, right? So the pressure ratio, there is a change in pressure. This is because of the viscous interaction. This is what I said, when there is a change in pressure, then it affects the drag force, lift force, and the moments and other stability parameters, right? So the boundary layer on the hypersonic vehicle can become so thick, and that it essentially merges with the shock wave, right? And merger shock layer, right? So here, when this happens, the shock layer must be treated as fully viscous layer, right? Because you know that the thickening of the boundary layer creates such effect, and the viscous interaction makes this in such a way that the shock layer must be treated as fully viscous, and the conventional boundary layer analysis must be completely abandoned. We cannot use directly the conventional boundary layer, right? So this is what the viscous interaction is. Um, okay, I will come back with the summary that there is we start with the boundary layer, and we have a thermal boundary layer, and there is a boundary layer because of the velocity. So the kinetic energy on the air, which is really very high, which is in very high velocity. So the kinetic energy necessarily converted into internal energy, and in our case it becomes a thermal energy. So the temperature on the surface becomes higher, right? The change in kinetic energy to the thermal energy, we call this as a viscous dissipation here. And again, because of the density based on the rho is equal to P by RT, we have the density change, and to pass the required mass flow through the boundary layer at a reduced velocity, the boundary layer thickness must be larger. And because of these two phenomena, the boundary layer gets thickens, right? And we talk about the laminar boundary layer thickness, right? And the boundary layer becoming thickening, and it creates a displacement effect, right? So the increase in thickness of the boundary layer interacts with the inviscid region of the boundary layer, right? That interaction is called the viscous interaction, right? So because of the increase in viscous interaction, the surface pressure also changes in the hypersonic body. And when there is a change in surface pressure, it in turn changes the lift force, drag force, and other stability parameters. So viscous interaction becomes an important hypersonic phenomenon, right? I stop at this point. Thank you very much for joining me. And in the next class, we will discuss about the effect of high temperature. Right now, we say that because of the boundary layer, uh, the boundary layer kinetic energy is converted into thermal energy, and how high it is, that we will see in the next class. Thank you very much.